Hello out there. Welcome back today. I hope you're ready. So we'll be looking at some counting principles in mathematics, okay? And remember to do your mathematics, guys. I really encourage you to have a pen and paper, and it's not about observing. You have to try to do some of the problem with us, okay? So let's see what we have for counting principle, okay? Sit there and hope you enjoy. So under counting principle, before we look at that, we have a quick question for you. I'd like you to think about it. What do you think, what is the probability of contracting a COVID-19? Can you really guess that? Surely yes. If you isolate, probably there's a low likelihood of getting that, but also it will depend in which province you are in. We've seen in some province a higher positivity rate, so a higher likelihood of getting the COVID-19. Are we together? So how can we calculate that? We can approximate it based on how many tests were conducted and how many people came positive with the COVID-19. We can really approximate that. But one can say, no, I don't think that's correct because I spend most of my time, I don't social distance. I spend most of my time at home, okay? I avoid large gathering. Surely you will reduce that. That is just an estimation. Fantastic, okay? Try to see that in your own province. Can you really calculate that? Look at that nationally. How does it look like? Okay, fantastic. So what are we going to look at under our counting principle? Also, what I'd like you to look at now is, what is the probability of winning Lotto? Sure. It's an interesting question. Can we really calculate? Can we actually win it? Yeah, we do have people that win Lotto, but what is the chance of winning it? Okay, I think for Lotto we have about 45 numbers. You have to get 6 correct to win the Lotto, the jackpot. So we need some counting techniques. How many combinations of 6 are there in 45 numbers? Sure. I think that's a large number. So we have to get 6 correct numbers. That's a jackpot. So I can go with 1, 2, 3, 4, 5, 6. I can select any 6. But how many? We have to think how many combinations of 6 are there. Okay. And how many you're going to bet. So it'll be how many you bet over the possible outcomes, which is a huge number. I'd like you to try that. Actually, if you play once, your number is close to 0. Okay, which is interesting. So when we look at counting, we're going to look at how do we really count that? Okay, fantastic. I hope that makes sense for you. I'd like you to try that, okay? Or if you have something, search engine, just search on that and see what is the chance of actually winning Lotto. Okay, great, fantastic. So we're going to look at counting principle as indicated, but under counting principle, we're going to look at choice with repetition. I'll talk about that later. What does it mean to have choice with repetition? Then from there, we'll look at introduction also. We'll start with that. Then fundamental of counting principle. Then arrangement without repetition. Okay, repetition with repetition. Just clear, okay? So some keywords. What is arrangement and what is counting? What do you think is counting? And what is arrangement? How do those two terms differ? Arrangement, I could have chairs and I have 3 people and I have to arrange how they sit. That's kind of an arrangement. But counting is the same kind of counting if I have to count number, 1, 2, 3, 4, 5. How many people in a classroom? How many people in a certain space. But that's not the kind of counting we're going to look at. It's actually more complicated than counting 1, 2, 3, 4, 5, and so on. Okay? Are we all together? Great. So arrangement is when I make arrangement, and counting when I count numbers, okay, or possible outcomes. It's another example of counting. So we will look at that further. So we're going to start now with introduction. So under introduction, let's look at this. Mathematics began with counting. Okay, we spoke about this. Initially, we used our fingers, beans, button were used to help with counting. Are we together? We could count from 1, 2, 3. We could use our fingers. We can use what? Button, and so on. That's the counting we know. Doesn't really differ from that. Okay. But this are only practical for small numbers. It's okay for a small number to use that. But what we have to ask ourselves, what happens when a large number of items must be counted? So this section, okay guys, will focus on how to use mathematical technique to count different assortment of items. Are we all together? Okay? Great. So when we started counting, we used our fingers, we used items, all those. But when you have a large number, how do you count? Okay? So we'll look at something of that nature. So let's see. An important aspect of probability, okay? So probability, we know probability, we're talking about chances. Is the ability to determine the total possible outcomes, okay? When multiple events are considered. What does it mean? Okay, so the question we started with about Lotto. So we have to ask ourselves, how many combinations of 6 are there? How many are there? It's quite a lot. Let's think about it. I can give you one combination now, which is 45, 45, 46, 47, 48, 49, 50. That's one combination. But how many combinations are there in the Lotto? Okay. So that's another way of counting. So for example, what is the total number of possible outcomes? Let's look at something small like this. When a die is rolled and a coin is tossed. Okay, so what do we have to ask ourselves? We have a die and we have a coin. Okay, are we all together? So a die has 6 possible outcomes, which is 1, 2, 3, 4, 5, 6. Are we all together? But a coin has 2 possible outcomes, which is head and tail. Are we all together? So what I have here, I have a coin, and what else? A die. A coin has 2 possible outcomes, which is tail and head, denoted by H and T. What about a die? A die has 6 possible outcomes, 1, 2, 3, 4, 5, 6. If I roll the 2 simultaneously, are we all together? That's what we're going to see what happens. Okay, so if we roll this, how many possible outcomes are there? So let's look at this. What is the total number of possible outcomes when a die is rolled and when a coin is tossed? So to do this, the roll of a die has 6 possible outcomes. We did say it's 1 all the way to 6. And a coin has 2 possible outcomes, which is H and T. Are we all together? So what does this mean? We could have 1 and head when we roll the 2. So if I roll a coin and a die, I could have 1 and head. That's 1 possible outcome. But also I could have 2 and H. A die could give me 2. A coin could give me head. So, and so on. 3 and H, 4, and so on. Therefore, there are 6 times 2 possible outcomes. How do we get that? Because how many outcomes for a die are there? 6. And how many for outcomes for a coin? We have 2. We have 6 possible outcomes for a die. We have 2 possible outcomes for a coin. Then we multiply the 2 and we get 12. Those are 12 possible outcomes if we roll a die and a coin simultaneously. Okay. Fantastic, guys. Okay. I hope this makes sense a little bit. When we come back after the break, we'll look at more fundamentals of counting principle. Stay there and enjoy. Welcome back once again, guys. Okay, so in our first, what we looked at, we had a coin and a die, and what we wanted to do was to calculate how many possible outcomes are there if I roll a die and also a coin simultaneously. We said a coin has 2 possible outcomes, a head and a tail, but a die has 6. And we multiply that by 2, which is 2 times 6. And we got that is 12. Are we together? So we had 12 possible outcomes if we do the 2 simultaneously. Okay, fantastic. So what we're going to look at now is to go and look at the fundamental principle of counting. Okay, what does that look like? So it's the fundamental counting principle. What is this fundamental counting principle? We can use list, table, and tree diagrams to work out the numbers of outcomes. Okay, are we together? Like listing. It was easy in the first example because for a coin, we only had 2 possible outcomes, and for a die, 6. So we can just list and see that actually there's 12 possible outcomes. But that can be difficult, especially if that set is large. Okay, so we have to find a way actually to do that in an efficient way. So using tree diagram can work, tables also can work, but this is only feasible. It's feasible for an event with few outcomes like the previous one. We had few outcomes because we had 2 possible outcomes for a coin and 6 for a die. That was okay, but for a large one, it's quite difficult. Okay. So when the numbers of outcomes grows, it is not practical. It's not practical to list the different possible outcomes. It becomes impossible. We could list in the first example if we have a coin and a die. We can list the possible outcome. We can say, okay, if I roll, I can get 1 in tail. That's 1 possible outcome. We can have 6, probably what? A tail. So it's easy to list that. But large becomes difficult for us to do this. Okay? It's not really efficient if we have lots of possible outcomes. So we'll have to use the fundamental counting principle instead. We have to use, what is this fundamental principle of counting? Let's look at that. It states like this. The fundamental counting principle states that if there are NA objects, are we together? Okay. In event A, and NB outcomes in event B, then there are N times B outcomes in event A and event B combined. What does that mean? I mean, it looks more mathematical, but let's break this down. If we have a die and a coin is event A, a die is event B. Are we all together? So the possible outcomes for a coin, it's what? 2. It's a number of event, 2. And for a die, 6, which is our NA times and B. Is the number of A and numbers in B. Are we all together? Fantastic. Okay. So, if we apply this principle, the fundamental counting principle, for our previous example had a coin and a die. We can easily calculate the number of possible outcomes by multiplying the number of possible dice rolls, which is what? 6, okay? With the number of what? Tossing a coin, which was 2. So the number of possible outcomes is 6 times 2, which is 12. That's the fundamental principle of counting. Are we together? Great, fantastic. Now, let's look at this. So another way of stating the fundamental of counting principle is this. This another way. If there are m possible outcomes, are we together? For event A, and n possible outcome for event 2, then the total possible outcomes for both events is m times n. That's the same thing. Similarly to the previous question, the number of possible outcomes for a coin is 2. The number of possible outcomes for a die, 6. Then m times n is 6 times 2, which gives us 12. Are we together? Fantastic. So let's look at an example here. A meal can be made up as follows. So here we have to choose a meal. So choice 1, it's meat, fish, chicken. Then choice 2, mash, you have mash there, chips, baked potatoes, rice, and vegetable. So the question is, how many different meals can be made using these choices? Okay, what does this mean? Can I take meat, mash, and chips? No, no, no. I have to select one from choice 1 and one from choice 2. Can I take meat, fish, then mash? Not allowed. You can't do that. But I can take meat, mash, that's okay. I can take meat and chips. I can take fish and baked potatoes. So you have to select one option from choice 1, another option from choice 2. So how many choices are there? Can you think about this? Okay, so if you look at this, we can try write some of the choices. Okay, so let's say, I'll say meat and mash, that's one choice, okay? But that'll take time. Meat and mash is one, meat and fish, it's another one, meat and baked potatoes, another one, meat and rice, another one, what? Meat and vegetables, that's another one. Fish and mash, fish and chips, fish and baked potatoes, fish and rice, and fish and vegetable. Yes, that's what we can do. But now, if we apply the fundamental principle of counting, so we're going to look at in choice 1. We have how many meal choices? In choice 1, we have how many choices? We have 3. And in the second choice, we have how many? Let's look at that. It's 1, 2, 3, 4, 5. So 3 times 5. Are we together? In the first choice, we have 3. Are we together? In the second one, we have 5. Then we multiply the 2, and we get this 15 different meals. Are we together? So you can try this without using the fundamental principle of calculus. You'll see that you'll get 15 choices which are available. Are we all together? That makes sense? Okay, fantastic. Great. So we applied the fundamental principle of calculus by saying in choice 1, there's 3, in choice 2, there's 5, and we multiply the 2, and we get 15 choices. Great. Looks easy, but there's so many choices there. Now, so what are we going to do now? We're going to look at choices with repetition. Okay. So, this is choice with repetition. What does it mean? Repetition, what does repetition mean? Okay. If I have to design a password for my cell phone, if I have to create a 4-digit password, I use 5555. I'm repeating 5. If I'm using 5666, I'm repeating 5 and 6. But ask yourself, is that password secured? How do you make that password difficult to crack or for someone to unlock your cell phone? So if I use different digits, it'll make it difficult and probably include some of the variables, some of the letters. It'll make it even more difficult. Okay. So what we're going to do here is count with repetition. What does it mean? Okay, we'll look at that. Let's see. When you have objects to choose from, so when you have to choose from, and you choose them from R times, the total number of possibles is what? Is n times n times n times n times n times n all the way. Okay, let's use numbers to make this easy. Let's say I have to create a password, 4-digit password, but I'm repeating digits. How many numbers do we have? 0 to 9. So we have 10 numbers. So if I have to repeat the first digit for my password, how many chances are there? It's 10, because I can repeat. For the second one, I can still use 10. For the third one, I can still use 10. For the fourth one, I can still use 10. So what does that mean? We're repeating some n object times n object times n object. If you multiply this r times, we'll get n to the power of r. That's the meaning of that. Are we all together? Okay. Fantastic. Okay. Hope this makes sense. So with the password, let me look at the password. Let's take a password. Let's use numbers. So let's say I have a password to design. And I have to use numbers. So this will represent what? 10, agreed? Because there's 10 numbers, and this will represent 10, this will represent 10, all the way to the power, this will be 10 to the power of r, if I have a large password. Okay. Okay, now let's look at another example. But this example differs slightly from the previous one, because the previous example, we only had 2 choices. We could choose some meat or something, and with a starch. But this example, we have 3 choices, okay, which we have to choose meat, fish, chicken. And the second choice, we have to choose mash, chips, baked potatoes, rice, or vegetable. What is added here? It's a dessert, ice cream, cake, or jelly. Are we together? So now the question is, how many different meals can be made using these choices? Okay, fantastic. So the previous one, I could do that from my head because I only had choice 1 and choice 2. And choice 1, you had just 3 choices. I could do that from my head. How we got that 15, I could have done this and said meat. Meat can go with mash, chips, baked potatoes, rice, and vegetable. So meat has how many combinations? 1, 2, 3, 4, 5. So meat, I can choose 5. Fish, similarly, I could choose mash or chips, baked potatoes, rice or vegetable. So there's also 5. Chicken also, there's 5. Hence we got the 5 for that and the 5 for that and the 5 for that, which gave us 15. But by the fundamental principle of counting, we don't have to physically count and combine this and combine this. What we can do is what we did, we just choice 1, multiply by choice 2, which was 15. Now we have 3 choices. Can we apply the same principle? What do you think? Okay, let's look at this first. So here, meat, I can take meat, mash, ice cream. That's one choice. This looks more difficult if I have to do it from my head without using the fundamental principle of calculus, of counting. Because meat, I can take meat, mash, ice cream. But also I can take meat, chips, and still ice cream. How many choices are there? It looks, can we really find all of them without using the fundamental principle of counting? I think that will be difficult, but we can. But if we apply the fundamental principle of counting, what we can do is choice 1. How many choices are there here? We have 3. So for choice 1, we have how many choices? 3. So we'll have to say 3 because we have meat, fish, chicken. For choice 2, we have 3, 1, 2, 3, 4, 5. Then we have 5 choices. We multiply by 5. And choice 3, we can take ice cream, cake, or jelly. So we have 3 choices. And we multiply that. 3 times 5 is 15. 15 times 3, we have 45 choices. So what we did is choice 1 times choice 2 times choice 3. Okay, so we'll end from here, and we'll see you shortly. Welcome back again, guys. We're still on counting principles, and I'm hoping that you're working hard at home there and you're trying your best. Okay, so under our counting principle, now what we're going to look at is arrangements where we're going to repeat letters, so we repeat numbers. Okay, let's look at what that looks like. Okay, so this is choice with repetition. Okay, so when we have n object, okay, let's look at what that means. So having n objects, okay, so n represents the number. I could have 7 chairs. Are we together? Then if I have 7 chairs, my n is 7. Are we together? So I have n objects to choose from them, and there's r times. Does that make sense? Then the total number of possibility is n times n times n times n all the way r times, which is n to the power of r. Okay. Let's try and make this simpler. If I have to select a password, okay, with what? Let's say 4 digits. So a password with 4 digits will look something like that. The first digit there, the second digit, third digit, and the fourth digit. If I have to choose numbers, my password is based on numbers. How many numbers do we have? We have 0 to 9. Those are 10 numbers. If I can repeat my password, so the first digits, I can choose, I have 10 possibilities. And for the second digit, I still have 10. For the third, 10. I'm repeating. 10. So what does that mean? So for my password, I can have 5555 because I'm repeating the digits I'm using. Are we all together? Okay. But surely that's not a secured password. Okay. So if I don't repeat, it's something different. Let's look at what we have. So how many different ways are there for predicting the results of 6 soccer matches when each match can end in either win, okay, lose, or draw? So there's 6 games. Are we together? So the first game, let's see, we have 6 games. This is the first game, second, third, fourth. Okay, that's the 4th, 5th, and the 6th game. So the first game, it can, when the matchup is, can either be win, lose, or draw. So how many possible outcomes are there? So it's 3. Because it's win, lose, or draw. What about the second game? It can also be win, lose, or draw. So there's still 3 possible outcomes. The third game, similarly, 3, 3, 3, 3. Are we together? So because of win, lose, draw, there is 3 possible outcomes for each and every game. And what we have to do is to multiply this together. So we multiply this together, and what do we get? We get 3 to the power of 6. Same base, we add exponents. You can leave your answer like that. Okay, use your calculator and see how many possible outcomes are there. Are we together? But a game like tennis, there's no draw in tennis. It's either win or draw. Are we together? So if there's 6 tennis games, it'll be 2 to the power of 6. Are we together? And just depends. If this is a league, because you can win, lose, or draw, but those who watch sports, if you look at quarterfinals, elimination stage, it's win or lose, nothing else. Are we together? So it's important that you read your question. Okay, fantastic. So now, what we had to do here, it's very important to read. Determine how many outcomes you have. It's very important that you read. Choose from each event, okay? So what we had here, we had 3 outcomes from each match. Win, lose, or draw. So you could have a situation where it is win or lose. But this, we have 3 outcomes, win, lose, or draw. Are we together? Then from there, determine the number of events. There are 6 matches, because those are 6 events. Are we together? If there were 5 matches, it would be a different story. If there's 3 matches, it would be a different story. So because it's 6 matches, then we can have that. Then from there, determine the total number of possible outcomes. And this is what we had. We had 3 times 3 times 3 times 3 times 3 times 3, which is 3 to the power of 6. No need to simplify that number. Okay. Or you can put in a calculator. You'll see what you get. Great. Now, a debit card. You know what is a debit card? Okay. It's a bank card. It requires a 5-digit personal identification, or a PIN, or a password. Are we all together? Okay. Consisting of digits from 0 to 9. Are we together? So you have a card. You create your own password. Okay. You can change it any time. So from 0 to 9, how many numbers? We have 10 numbers. So the digits may be repeated. How many possible pins are there? How many pins can I create, exist? How many? So let's start. So we have to create a 4-digit password. So there's the first box. There's the 4-digit password. Are we together? With this 4-digit password, how many numbers can I choose from there? I have to repeat. So I can put 10. Why 10? Because I can choose from 0 to 9. 0 to 9 is not 9 numbers, it's 10 numbers because it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Are we together with a 9? 0 to 9 is 10. Are we together? 1 to 9 is 9 numbers, but we can use 0, therefore we have 10 numbers. So I have 2 possibilities for the first digit. I can choose any. And the second one, I can still choose 10. Third one, I can still choose 10. Fourth one, I can still choose 10. Then how many possibilities are there in total? We just have to multiply. And what do we get? 10 to the power of 4. Those are the possible outcomes. Fantastic. Then what you can do, you can leave your answer in exponents like that, or you can put that on your calculator. Fantastic. Okay, so now let's look at another example. The province of Gauteng ran out of unique number plates in 2010. Interesting. Prior to 2010, the number of plates formulated using the style LLLDD-GP, where L represents the letter, agreed, of alphabets, excluding the vowels. So we have 5 vowels, okay, and the Q. So vowels and Qs are not used on the number plate. Are we together? So if we exclude the vowels, we're left with 21 letters. Are we together? Then if we remove Q, we're left with 20 letters. Are we together? Okay, so we have 20 letters to use from. Okay? Then D represents the digits between 0 and 9. Are we together? That's D. The new style the Gauteng government introduced is LLDD-LLGP. So the question now is, how many more possible number plates are there using the new style compared to the old style? Let's find the new style. Because we can repeat, L represents the letter. So for LL, we'll have 20 times 20 times 20. For D, which is the letter, which is a number, we can have 10, 10, 10. Are we together? So this is all possible for the old style. And the new one, L is the letter, are we together, which is there. L will have 20. And for that, that's 20. And D represent what? D represent a number. So we can have 10 times 10. And we can have a letter there, which is 20 times 20. So from here, what you can do, you can get the value for that. And what you have to do, it's okay not to simplify in counting principle. So to do this, we have to minus the 2. Are we together? And I can write this in exponent form. If I write this in exponent form, I get 20 to the power of 3 times 10 to the 3. And this is 20 to the, what? To the power of 4 times 10 squared in exponents. If I minus the 2, I'll find how many more number plates I have. Okay. So I hope this makes sense. So there's other provinces, they've never changed even combinations of number plate. I want you to think about which province. And why does Gauteng, they ran out of combinations of number plate? What do you think? Could be the population. Okay? Fantastic, guys. Hope you enjoyed now. So we're going to take a short break, and when we come back after this, we're going to look at more counting principle questions. Enjoy. Welcome back again, guys. Okay, hope you're ready and excited and pushing hard, and it's okay to be challenged. Okay, and it's okay not to understand something. But what is important is just to keep working hard. We're still on counting principle. Okay, and let's look at what we have now under counting principle. So now we have a question there. Still arrangements without repetition. So 8 athletes take part in 400-meter race. Okay. So now, in how many different ways can all 8 places in a race be arranged? So is this a repetition? We have 8 athletes, they're racing together. Only one person will be position 1. Another person will be position 2, position 3, position 4, 5, all the way to 8. So you cannot repeat this. Not everyone can be position 1. But now, how many arrangements are there? Okay, let's see what we have. Because we have 8 places, so if we have 8 places, so we're going to have 8, the first place. How many possibilities are there for the first position? Anyone can take a position, the first position. So 8 athletes have a chance of taking the first position. Now, if the first position has been taken, how many people, athletes, we're talking about 8 athletes, can take the second position? How many? So already, one will have 7. Why 7? Because a person will have taken the first position. We can't have 8. You all can't be number 2. You all can't be number 1. Now, position 2 is taken. What about position 3? Position 3 will be 6 because 2 guys gone. 2 guys already taken what? 1 and 2. So the last 6 guys are fighting for what? They're running hard for what? For other position. Are you all together? Position 3 downwards. Now we have position 1, position 2, position 3. Now what do you have to do? Is from position 4. So position 4, number 1, one person gone, another person gone, another person gone, took position 3. Now, position 4, there's 5 people. Are we together? Then, followed by 4, 3, 2 guys left. Then, the last position, there's 1 person can take that. Then you multiply all this. This is the total arrangements which are available. Are we together? So you can see with this one, you cannot repeat in a way. As the race starts, all 8 athletes, they have a chance of getting position 1. Someone's going to run faster, take position 1. Only 7 guys left can take position 2. When position 2 is taken, you have 6 people who can take what? Who can take what? Position 3, and so on. And if position 1 to position 7 is taken, only 1 person left who can take the last position. You can leave our answer in that form, which is 8 times 7 times 6 times 5 times 3 times 2 times 1. Or you can put that in a calculator. When you do counting principle, it's not really important to get the actual answer, but this is the answer. Just show. It's better to show your working out than just typing the answer. Are we together? Fantastic. So now, another question. So 8 athletes take part in 400-meter race. In how many different ways can the first 3 be arranged? Yes. Now, during Olympics or a race, you get 3 medals: silver, gold, and bronze. So we still have 8, but now, how many possibilities are there? So there's 3 positions now. But there's still 8 athletes. So there's 3 sports. 1, 2, 3. As the race starts, how many athletes are there? So we have 8 athletes. They all have a chance of taking number 1, which is all 8 of them can take number 1. Then if number 1 has been taken, then what about position 2? 7 guys can take position 2. Only 7 left. If position 2 is taken, how many can take position 3? Only 6. Then what is our answer? Which is 8 times 7 times 6. And that is our total. Okay. Arrangement. Are we all together? So this can be a repetition because you can't have all being number 1, number 2, number 3. Okay? So we need one number 1 number 2, 1 number 3. Okay, we're all together. You can't take 2 places during Olympics game. Okay, or during a race or 400-meter race and so on. Fantastic. So now, let's consider the word sentence. Okay? You are required to form 7-letter word. Yes, a 7-letter word. Sentence is 7-letter word. 1, 2, 3, 4, 5, 6, 7. Okay. Arrangement using the letters of word sentence. So we just have to word using sentence. An example of a word arrangement will be something like this. It doesn't have to make sense. So just I have sentence, it's words. So how many arrangements can I arrange are there with the word sentence? So it does not have to make any sense. So this is an example where actually here, if you can see, we switched some of the words there. It doesn't have to make sense. Let's see. So this arrangement of letter need not to make sense. So the first question is, how many possible word arrangements can be made? Okay? The letters may be repeated. So the letter may be repeated. So the letter sentence is what? 7 words. So what does it mean? 7 words. So I can have 1, 2, 3, 4, 5, 6, 7. Okay? So for the first position, how many choices are there? I can choose 7. I can repeat S. For the second position, I can still repeat. I can still choose 7. For the third one, I can repeat. I still have 7 choices. Fourth position, I still have 7 choices because I can repeat the letter. Similarly, I can repeat. I can repeat. What do I get? If I multiply all this, what do I get? 1, 2, 3, 4, 5, 6, 7. So I get 7 to the power of 7. Okay? 7 to the power of 7 like that, it's okay. Because I can repeat the letter. If I use the letter in the first position, I can still use it again. I can still use it again. Okay? But what I want, the string of my letter is to be 7 long. Are we together? Fantastic. Now, let's look at another question. So, still the same question. Now is, what if, still the letter sentence, okay? So we have the letter sentence, which is 7-letter word. Arrangement using the letter. We want to make arrangement using the letter. Word sentence, remember, does not have to make sense. The meaning. So how many possible word arrangement can be made? Are we together? If letters may not be repeated. So sentence goes 7-letter word. So if you have used S in the first position, we can't use it again. We can't repeat it. So how many arrangements are there? Let's see what we get. So we have 7-letter word. Let's look. 1, 2, 3, 4, 5, 6, 7. So the first position, we can use 7 because it's 7-letter word. Now we have used the first, we have used 1 letter. So we left with how many? 6. Now we have used 6 letters from 1. From the 7, are we together? We left with 5 to use in position 3. Then if we have used 5, we have 4 to use. And if we have 4 used, we have what now? 3. Then we left with 2, then 1. What do we have to do is then multiply that, multiply that, multiply all that. So that will be 7 times 6 times 5 times 4 times 3 times 2 times 1 without repetition. Are we all together? Fantastic. Okay, hope this makes sense. So, in how many ways can 6 different people be seated in a particular sit in a movie? So this can't be, you can't repeat, because you have 6 chairs, 1, 2, 3, 4, 5, 6 chairs. So the first chair, 6 people can take. Second chair, 5, 4, 3, 2, 1, and you multiply this. This is the same question as the kind of Olympics game. Okay. Hope this makes sense? Okay. Are we together? Because you're in a movie, you can't repeat. 6 people can take the first sit, 5 and so on. Fantastic, guys. I hope you enjoyed our lesson and keep working hard at home, and we hope to see you soon.